Everybody for joining us today. In this session, we'll be discussing hood design. My name is John Dano. I lead our corporate efforts here to partner with engineering firms at Donaldson Company. We also have Amy Miller, who's with us today. She's our training manager. She'll be working behind the scenes as she has been here, moderating the Q&A session at the end. So we understand all the complexities associated with dust control, especially specifying airflows. So that's why we do these webinars, so everyone understands the basics of dust collection and what resources you have at your disposal. So today's webinar, again, will just focus on one aspect of dust collection, proper hood design. Again, it's complicated, so sometimes we break it down into different elements to make sure we're getting a little deeper dive into certain areas of dust collection. We're going to start off today's webinar talking about the basics of dust collection, including the fundamentals and calculations that pertain to hood design. Then we'll get into different types of hoods, how to calculate hood losses. We'll show you some examples of good hood design and some common mistakes to avoid. And then we'll finish up at the end with everybody's favorite part, the Q&A session. So in case anyone's not familiar with Donaldson Company, we've been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first tractor engine filter. Today, we're one of the largest providers of unique filtration technologies. We excel at producing high-quality filters and equipment. We pride ourselves on having a global reach with a local touch. Our world headquarters is here in Bloomington, Minnesota. We have about 56 manufacturing plants and about 22 distribution centers around the world. So as you think of questions today and throughout the webinar, please type them into the chat box. We'll make sure we answer them towards the end of the session. And during the webinar, John may ask you a few questions. You'll respond with a thumbs up or thumbs down. You can access these by clicking the face icon at the bottom of your screen. So I'm pleased to introduce our featured speaker today, John Schmidt. He's a territory manager with Pearson Arnold Technologies, who is our local sales representative in the Minneapolis, Minnesota market. He's been in the dust collection industry for 13 years. He actually used to be an engineer here in the Donaldson team before moving to the sales side. He has a bachelor's degree in civil engineering from the University of Minnesota and an MBA from Argosy University. He's also a youth football coach and served our country in the Marine Corps. And with that, I will turn it over to John. I think you're on mute, John.
All right, thanks a lot, John. I'm going to shut my camera off so things don't get glitchy as I speak. Like I said, thanks a lot. We'd like to start out by asking about your experience with designing hoods for dust collection systems. So based on what you've already done or are currently doing, select an emoji that kind of aligns with your experience level so we can get a good idea of kind of what we're working with as far as what people are familiar with.
It looks like we have a few people with a little experience, some pretty, some very experienced. So you have a good mix of none to very experienced, John, full spectrum.
Good, excellent. That's great. And as it goes, like John said, I've been doing this for about 13 years and I still come up with new applications and hood designs regularly. So it's a continually growing process here, but let's start with the basics of dust collection and how that relates in your overall system design. The important reasons to control dust, fume, and mist in your processes are safety concerns and hazards, improving the air quality for employees, exposure control, reducing potential dust in the breathing zones of the workers that operate these processes, environmental concerns, EPA standards for outdoor exhausted environmental air quality and outlet emission requirements, and lastly, cleanliness, concern about the overall cleanliness of the facility. So this is a typical dust collection system illustration. A fan creates an airflow through the system, which captures dirty air at a hood, then conveys the material through the ducts into a dust collector. There, the contaminant is separated out, clean air passes through the filter media to the fan where it's discharged to the atmosphere. You can see a few hood styles shown in the diagram, hood 1 is pulling the air from the side away from that operator, and then hood 2 is pulling their dirty air straight upwards. If one component in the dust collection system, such as a hood, in this case, is poorly designed, the whole system is affected. When we design systems, there's a lot of factors that are considered, probably more than most people realize. The publication shown in this picture is the Industrial Ventilation Guide, written by the ACGIH, which is a nonprofit scientific organization that advances occupational environmental health. The guidelines in it are considered by most of the industries, including OSHA, as the standard for proper ventilation design. The ACGIH offers multiple courses throughout the year on system design using the Vent Guide as a textbook. I've attended multiple courses myself over the years. If you want to get more information on system design, I recommend that you also check them out. And this would be a good spot if anyone's ever been to the event conference or another ACGIH industrial event conference or training. Give us a thumbs up so we kind of know if anyone's been through some of that training.
Well, I'm not seeing any. Oh, there are a few. All right. All right. A couple. It's a great resource, as we mentioned, identifying those resources, and it is kind of the guidebook that we use for a lot of our system design. So definitely keep this in your back pocket and use it as a resource. Thanks.
Yeah, absolutely. And I think there's 3 standard event conferences across the United States. They're all a week long that are offered every year. They have other classes, but if anyone gets the opportunity, it's definitely a time well spent. There's a lot of different formulas that we use in system design, but the most basic and widely applied being airflow. And the formula that we memorize for this is Q equals VA, where Q is a volume of airflow through the system. We use CFM, or cubic feet per minute in America. To get the airflow, we multiply the velocity of the air by the area of the hood or the duct that the air is flowing through. So velocity times area equals volume. This formula is one of the basic building blocks of dust collection system design. We start at the pickup points and calculate using this formula to get the needed airflow of each pickup through the duct and give us a total CFM needed for the system. This formula is also used when calculating the needed velocity within the ductwork. Throughout the design of this system, we refer to this as Q equals VA over and over again. And I guess the biggest other little bullet point on this is that the difference between dust collection ducting and standard HVAC ducting is that when you're handling dust collection dust, you're pneumatically conveying a material as opposed to moving air. So that's why this Q equals VA becomes so important. Few other basic terms that we use in hood design is the face velocity, which is the speed of the air crossing the entry plane of a hood. The capture velocity, the speed of air necessary to control the direction of the contaminant at the hood entry. And then static pressure, which is the resistance to airflow that must be overcome to keep the air moving through the hood and the ducts. In the United States or North America. In Europe, you might see millipascals, but we use inches of water gauge as the standard industry term in the United States. So let's get into the hood design. It's typically the first component you size when you're designing a new system. A well-designed hood is going to minimize the amount of airflow that's required to effectively capture and control the contaminant or is released in order to protect workers. It should be designed with good ergonomic principles in mind. It should be compatible with material flowing through the work area, and it should be designed to minimize maintenance and other activities that may disrupt the process. A hood must be positioned properly relative to the point where contaminant is emitted in order to be effective. To minimize air volume, the hood must be close to the capture point, but not so close that it's disrupting the process. A hood position twice the distance from a contaminated emission point rather than at the capture point will need to draw approximately 4 times more air to produce the same capture efficiently. And of course, more air means larger collection equipment, larger ducts, larger fan, higher horsepower, all of which adds to capital and operational costs. In the picture here is a portable weld fume collector. The hood is positioned close enough to capture the fume and pull it away from the operator's breathing zone, but far enough away to not disrupt him or the process. Here's another example of an effective hood location that Weld.com did using a training video with one of our weld fume collectors.
Until we get it right. Until we get it right. Until we get it right. Until we get it right.
All right, in terms of airflow at the hood, there are some examples of, these are some examples of capture velocities, which vary based on the application and the dust, fume, or mist being generated. And this list comes right out of that industrial ventilation manual that we talked about, that book a few slides ago. And the very top would be typical for weld fume, kind of like we just saw in the video. We're talking 50 to 100 feet per minute. It's light, easily flowing dust that isn't being forcibly moved. And at the very extreme end of that would be grinding, tumbling mills. If we do like bead blasting equipment or grinding wheels, or where the dust is being forced away. And if you have a high-speed grinder or a bead blasting gun, then you're talking upwards of 2,000 feet per minute. And everything else typically kind of falls somewhere in between. So in the vent manual, we're going to see some formulas on how to calculate airflow at the hood. This one's pretty simple. You take the distance from the hood face to the furthest point of contaminant release, square it, and multiply that by 10. Add the hood face area and multiply that by the capture velocity. That sounds like a lot, but it's pretty simple. We can do a quick example here on the next slide. The hood has a 2 foot by 4 foot opening. We have defined our capture velocity requirement at 100 feet per minute, and we're 2 feet from the source of generation. If you run the math, you're looking at an airflow requirement at the hood of 4,800 CFM. This one's pretty simple. It sounds more complicated than it really is. It's a pretty simple formula for this one. All right, so why is this important to get to calculate the airflow at the hood? Well, there's problems with too much or too little airflow. So too much airflow at the hood or the pickup point may mean you're picking up good product rather than just the nuisance dust. It could also increase your risk of capturing unwanted material like sparks or embers. Since more energy is required to move the airflow, it then leads to higher than expected operational costs, bigger collector, bigger fan, etc. And then the opposite is a problem too. Not enough airflow at the hood means you're not capturing all the dust effectively. Then the dust that may lead to it includes risk of employee exposure or just poor housekeeping. So we'll talk a little bit about some different types of hoods. At a very high level, there's 2 main types of hoods. There's an enclosing hood, which are essentially ventilated boxes that completely or partially envelope contaminant during the process. Although it's the most effective hood style, they can somewhat limit operator access to a process, so are not as common in dust collection systems as we'd all like to see. This is an example of an enclosing hood over a robotic weld cell. Since it's a robot, it's really easy to enclose the entire process, but that's not always going to be the easiest case. 'Case. For welding, you may see large capturing hoods like this, often with curtains around them for weld stations. We do a lot of testing at Donaldson, so we thought it would be fun to show a few videos from our fume hood. The video in the middle is using a smoke machine when the hood was being tested in the lab, so it would simulate robots welding at the same time. The video on the right is showing just one weld station where small amounts of weld fume are being emitted and cleared. Capturing hoods rely on a flow of air into the hood opening to carry the contaminated air into the hood. This type of hood is much more common and allows the operator access to the process. It's not going to be as effective as a fully enclosed box, but if designed correctly as part of a well-engineered system, they're effective at capturing the fugitive dust and protecting workers. The four most common types of capturing hoods, in order of increasing effectiveness, but also increasing fabrication costs, is the raw edge hood, flanged hood, tapered, and lastly a bell mouth. So we can talk about each one in a little more detail to kind of help determine which one you want to specify on any particular project. Give us a thumbs up. This is a good spot to get some feedback to see who's spec'd in or designed in any of these types of capturing hoods in their projects. A lot of thumbs up. Good.
Yeah, a lot of thumbs. Yeah. All right. Yeah, it looks like you have a lot of thumbs up there, John.
Yeah, I think that's got to be about everybody, and maybe then some. That's great. That's really good. So at the very first, we call a raw edge hood, which is even really a hood. A raw edge hood is just what it looks like, the cut end of a duct. It's going to be the least expensive and simplest option. However, there's a lot of static pressure loss going in, and it's going to be the least effective at actually capturing dust from an area around the opening. So you're saving the customer money on the hood, but at an increased static pressure, which would result in a larger fan, and it may not provide the needed capture efficiency. We don't recommend specifying a raw edge hood. Usually where you see them is where maybe the actual design hood fell off, or kind of a DIY job where the customer buys a new tool and just taps into an existing duct and puts a length of pipe on it and points it towards the direction of the dust. Not necessarily recommended for most applications. A flange hood is a step in the right direction from a raw edge. It basically puts a face across the edge of the pipe. Still inexpensive and simple, but still has a pretty high static pressure loss and is not extremely efficient. Generally see these when tapping into an existing enclosure, so the enclosure surface becomes the flange penetration point. Here's an example of what we consider flange hoods. These are large woodworking CNC equipped router. The flange hood connects to what is essentially an enclosed woodworking CNC machine. So it kind of becomes an enclosed hood at that point, but the flange connection kind of creates a combination of a flanged hood with an enclosure. A taper hood is something we see a lot more often. It does a really good job of giving you better distribution of airflow and increases your capture efficiency. We use these when we're connecting a piece of equipment or material transfer points. When you're trying to spread the airflow across a greater distance or larger area, they can carry it back to the duct. This is an example of a transfer point on a screener or tumbler outlet. You can see it's kind of tricky to see, but if you look past it upside down Y and see that it's like a screener or a tumbler where material comes down into a transfer point, then there's a tapered hood at the top of that transfer point where it comes out to capture the dust. What this is also doing in addition to creating a more efficient airflow is that that transfer, or that tapered hood creates a larger area, which air to collect the dust from. And what that does is, we remember that formula we just talked about, Q equals VA. So if the air in that duct is moving at, say, approximately 4,000 feet per minute, which would be pretty typical, or if you quadruple the size of that opening at the end of the taper, you reduce that airflow significantly. So what this does is makes it more efficient by reducing the airflow, but it's also only capturing the fine dust and not capturing the good product. So that if we reduce the airflow to under 1,000 feet per minute, we're still going to capture the fugitive dust, but we're not going to capture the good product coming up, because we want to make sure that we're not sucking good product into the collector. And then by the time it gets up into the duct, it's just the dust, and then it gets sped up to your carrying velocity, which application like this is probably around 4,000 feet per minute. Excuse me, a bit of a cold. Here are examples of tapered hood used in rail and truck dump pits. Dust generation is highest when the gate is first opened on the bottom of a hopper trailer or rail car. You always want to fully open the gate to choke feed the dump pit. And basically what that means is that the pile of, whether it's grain, typically we see these a lot in grain, but you also see them in minerals for unloading trucks of, or it could be plastics for a plastics company. As the material flows through the opening, it's reducing the open area of that grading. So again, just kind of repeating the same formula, we're using that Q equals VA. So if we close off 50% of that graded opening from the material flowing through, and we have that pit grading size for, say, 100 feet per minute, which would be pretty typical for a truck receiving pit. If 50% of that opening is closed off by material flow, now the velocity essentially just doubles because of that Q equals VA. We've cut that area in half. But we're pulling the same amount of volume, so now the velocity is going to increase. If the pit's deep enough, you can utilize under the grate ventilation, like the one on the left. So with a deep enough pit, you have like small duct sections that go to essentially a tapered hood to pull the dust up and out. Under the hoods have to be located far enough away from the grain pile so the product isn't picked up. And there are there's some companies that make truck receiving or rail receiving pits, like in this case, that specifically have baffles designed or dropout areas to keep the good product from getting picked up. If the dump pit's too shallow, or maybe there just isn't any duct work available underground for it, we can utilize the great draft style hood, like on the right. The hood needs to be located as close to the hopper as possible and on both sides. So we typically see around 10,000 to 15,000 CFM on something like this, because it's having to draw air from multiple points, as opposed to the one on the left, where we're probably under 10,000 CFM, probably somewhere 7,500 to 10,000 CFM, depending on the size of the opening. Here's a few examples of taper hoods used on belt conveyors. Face velocity and capture velocity need to be sized to control the dust in the application. And where you'll see the sizing guidance for the capture velocity and the airflow, again, is going back to the ventilation manual. They will give you guidance on what the airflow requirements are, or recommendations are, based on, typically it's the width of the belt and the belt speed. And it's pretty clear cut, simple. Width of the belt speed, there's a simple formula that'll give you what your airflow is, and then we design a hood for that using those same principles. And this is another case, kind of like we talked about on that tumbler or screener, that the duct opens through a tapered hood into the belt enclosure or the conveyor enclosure, and for the same reason, that's to slow down the airflow directly over the material on the conveyor, because you don't want to, you're only trying to capture the dust that's in the air. You're not trying to capture any of the material that's being conveyed. So slower velocity through that hood, that speeds up when it gets into the duct. The last type of hood, the one we use the most, is called a bell mouth hood. It's readily available from multiple manufacturers. They will often have, a lot of times manufacturers put lights on the end of them if it's for a point of use application. They're going to typically be the most expensive of all the options, but they're also the most efficient. We see these very often on the end of weld fume arms and when you're capturing particulate from an open process. And the basic idea of a bell mouth, if anyone's familiar, it's basically the same as the end of a trumpet or a brass instrument. And it's very efficient at moving dust coming into it for the same reason that they're selected for sound on a brass instrument leaving them. These are also recommended for even if you're doing like ambient weld fume, and sometimes you see square duct. That's where you typically see a raw edge opening, is on a like an ambient weld fume capture, where you just see a raw edge, whether square or round, sticking up from a big duct. Replacing those with bell mouths has a substantially improved efficiency of capturing that ambient dust that's in the atmosphere. This is an example of a source capture weld fume installation that's coming together. You can see floor mount stands that help position each of these hoods in the right place. A series of booths we built around each of these stations, or will be built around each of these stations, but this is what it looks like when putting together a system for a shop with multiple stations. So you can see all these individual different weld stations with their own hood to capture the weld fume. This is another example, but you can see where the partitions are built in place with the arms so they can work wherever they are inside of the booth and then keep the hood over the top of the application. These are specialized capturing hood types. This is what's called a slotted hood, and these are also common for weld fume capture. You can see in the pictures, it has little open slots which create a high velocity area where the dust or fume is directed into the hood. The one on the left is like a little booth enclosure. And the picture on the right would be an overhead fume capture system, where again the high velocity of the slots motivate the air into the hood. You also may see something similar to the one on the right that's really common, is where you put a big hood over the top of, say, a robot welder, or sometimes you see them over the top of a small plasma cutting table or weld area. We put what's called, if it's say it was a large hood like you would see in the picture on the right, you would put you would have a big rectangular opening, what's called an impact plate, which is just a flat plate on the inside of the hood with about a 2-inch open perimeter around the edge. And it has the same effect as these slotted hoods, where it's going to capture the weld fume as it comes up, but then around the perimeter, there's a high velocity area to pull the dust into the hood. But since it's such a small area, such a small width, you can capture a big area of welding using a very small amount of air, which again keeps smaller duct, smaller dust collector, smaller fan, etc. There's a lot of different custom hoods that come into play. That little red box in the middle of this cutting machine was fabricated and attached to a piece of flex duct, so it moves with the cutting head, so that it captures the dust as the material is being cut and pulls it into that flex duct. All right, now we're going to talk about some static pressure loss. So calculating hood loss is pretty simple, especially for these easy hoods that we work with. You can see the formula on the screen. You just take the hood entry loss factor, add in the acceleration factor, which is typically 1 inch, and multiply it by the velocity pressure of the duct. We'll see a quick example here. Let's say you're designing a simple hood for a system that requires a transport velocity of 4,000 feet per minute and an airflow of 3,000 CFM. The velocity pressure is a factor of velocity in volume, or CFM. This image is taken from a duct calculator that I like to use, but you can get this from the vet manual, or your company may have your own spreadsheets or databases available. In this case, the velocity pressure factor is 1 inch of water gauge. And you can see where that lines up. So 4,000 feet per minute, 3,000 CFM, and then 1 inch of velocity pressure below. To show you how hood type makes a difference, a raw edge hood adds the highest amount of static pressure to the system at almost 2 inches of water gauge. Flange hood is better at 1.56. The tapered hood is an improvement at 1 1/4, and the bell mouth hood is going to be the best at about 1 inch. And that little graphic on the bottom right shows you, I mean, really where the difference between a raw edge is almost double the amount of restriction from a bell mouth. So that's kind of a good example. And by the way, if anyone doesn't have one of these ductulators or they need one, just let us know. We'll be happy to get you one.
Yeah, my email will be at the end. They can just send me an email and I can get one mailed out.
Excuse me, the vet manual also has many different types of custom and complex hood to help you determine the CFM and static pressure at the hood. This is an example of a grinding wheel hood. As you can see, there's a table available to determine the airflow based on the width of the wheel, and ultimately helping us determine the amount of static pressure for this type of hood. So that's kind of the tip. There's a whole kind of catalog of these different types of commonly used hoods in the industry. Here's a couple of other types. This is for a surface tank or a batch mixer that's producing dust that needs to be contained over the top. So again, it's kind of a what we call a long, narrow duct opening, which creates a high velocity draft to pull the air into the duct. This one is a movable exhaust hood, kind of like some of the pictures I showed previously for weld fume collection. And then a weld bench hood. Again, the vet manual is very useful for helping determine airflow and static pressure at the hood based on the application. And if you're looking like it, and we also have some products, for example, these are great tools that they show you how to calculate exactly what you need. But Donaldson, for example, makes a weld bench hood that has all this math built into it with prefabricated hood. Same with the extraction arms on the previous slide. We offer those same hoods as well, that everything's all built into the design. So I've been around this, like John said, for quite a few years now. So I've seen a lot of different systems. When I get called in to meet with a customer and take a look at their system, there's a lot of different things that I see, and I'd like to share kind of some of the examples of maybe where there's room for improvement. So I'm not sure what anyone can give a thumbs up if they see what's wrong with this particular picture, which isn't even necessarily uncommon. So looks like we're all getting it. So there is a weld fume extraction hood, and there's a welder that's welding, but the hood is behind him. And this is something that those weld extraction hoods are extremely effective when they're used properly. If you have a part that's on a jig that you're going to weld 200 parts of a day at a table, they're great because you can put that weld fume right behind the part, do your weld, and go through the systems. What we run into is job shops or larger project shops where welders are welding pieces that are 4, 5, 20 feet long, vertical welds, overheads, everything else. And they don't want to babysit that hood and bring it with them every time they move their weld, or it just gets in their way. So this is not an uncommon situation. A lot of extraction arms are designed or purchased and installed with the best of intentions, but if the welders don't use them, they're not effective. We have other options. We actually we've done some really good source capture weld fume with specialty made MIG guns that have the fume extraction built into the gun itself, and then we run a high static pressure system of multiple welders back to a single collector. Those are extremely effective. Again, the welder sometimes complains because now they have to use a different weld gun, and they might say it's bulkier or heavier until they get used to it. So then the next step would turn into do like an ambient weld fume filtration. And that's why, I guess, to summarize all that, is there's a lot of different ways to handle weld fume. So when you come into those type of applications, it's great to chat because we have a lot of different options depending on each specific application. Another big issue I see is inadequate airflow at the hood. In this picture, there's multiple pickup points, which is pretty common with an engineered system. Each hood is designed individually for a specific airflow. We're going to cover this more extensively in next month's webinar in duct design. But in this system, there are slide gates in each of the vertical drops that allows you to help balance the systems. Those things get adjusted and modified over time. People open and close them, and that can lead to poor performance with inadequate airflow because the system becomes out of balance when you have too much air going to one hood and not enough to the other. And then that going back to a half dozen slides ago where we talked about calculating the correct airflow for each hood. If the system comes out of balance, then we're going to be either too high or too low at each individual hood. And I guess one last thing on that last slide that would be important. It's a lot of times what I see with end users that helps a lot with this is actually two sets of slide gates. Typical, and that's like a woodworking facility. And it's pretty typical for a woodworking facility to have 4 times as many tools as employees. So you have but they all have a ducted system. So you're opening and closing them as you're using them, and then reclosing them when you're not using them. So what's often recommended is 2 sets of slide gates. So one slide gate typically up top where it goes into the main duct to balance the system, that gets set in place and left where it's at. And then you have a second slide gate near the tool that allows the operator to turn that particular duct off and on without unbalancing the system. This one is probably my favorite. Somebody took their tailgating tent and put a big tarp over the top to turn a porta trunk weld fume extraction arm into a ambient weld hood. The A for effort on it, I guess, but not an effective means of capturing the weld fume around this area, but a fun one to share. Well, designing dust collection systems can be complicated, and there's a lot that goes into it, but that's what we're here for. We've sold countless dust collection systems around the world. We have local support in your market, wherever you're located, and we're here to help to make sure that you get it done right the first time.
All right. Hey, thanks, John. Obviously, we talked just about hoods today. Obviously, there's a lot of other aspects to dust collection, including, ducts and collectors and controls. And those are the things that we break out and cover in some of our other webinars that are, readily available. And then we talked a lot about weld today, but we know obviously these same principles will apply whether it's in the grain world or the chemical world or laser cutting world. The same 4 principles will certainly apply. So we're going to finish up with some Q&A. John and Amy, if you can turn your cameras back on now, and we'll get into the Q&A. Just a heads up, everyone that attended will receive an email that includes your professional development hour credit. You can just send me an email if you don't see something within a week, but you should get that out there. Sometimes it winds up in your spam box and we got to resend it, but we can get that out there. There's also a few QR codes if you're interested into our event page for upcoming live webinars we have next month. And then we also have an on-demand page to cover some of the past recordings we've had, things regarding laser cutting. We also have webinars on combustible dust. We kind of break it out and cover deeper elements into each of the different aspects of dust collection. If you have follow-up questions, again, feel free to send me an email. If you need one of those ductilators, I can get one sent out to you. Just shoot me an email. And if you're also interested in registering for one of our in-person 5-hour sessions, we do have a couple of those scheduled throughout the country where we do a 5-hour fully credited session in a couple of cities around the country. The first time we're trying this, we've done a few in Minnesota, but we're taking the show on the road. Amy, we'll start it up with you going on to our first question.
Yeah, so I had a few sent to me privately, and then I'll look at the ones that are in the general chat box. John, how does someone know how close to put the hood to the process?
The short, it depends on the application, of course, but the short answer is as close as is applicable. And what that means is you want it close enough to capture the fugitive dust, but not so close that you're creating a problem with the system. And it's probably easier to just give a couple examples. We all talk about, we use a lot of weld fume examples. If you have the hood too close to the weld, you could potentially pull away the shield gas, and then that creates weld quality issues. So close enough to capture the fume, but not so close to suck away shield gas. If you have a grinding wheel that's grinding metal, you want it as close as you can possibly get to it, because all of the dust being generated on a grinding wheel is nuisance dust, typically 100%. So you want it close. And I'd say, some of the in-betweens are like a blast booth, where you want to be, you want to capture the dust of the blast booth, but you're not trying to necessarily suck all the blast media into the duct. So in the same, we talked about like the grain, like if you have a bagging system where you're maybe filling feed sacks or filling fertilizer bags or whatever the product is, same type of thing, as close as you can to get as much of that dust. In that case, you might do like a slotted hood where you're drawing the ambient air at 500 to 1,000 feet per minute, which is enough to capture the dust from filling the bag, but not so much it's not sucking the product into the hood. It's not a very definitive answer, but I hope that helps.
No, thank you. Appreciate it. So the next one, you showed that picture of the wood application, right? With all the different hoods involved in the system. Is there a way to test to make sure how do you know that it's still in balance? Is there a way to test each hood to make sure that it's still, it's got the right amount of capture velocity at each hood?
Yeah, absolutely. There's a couple ways to do it. There's the kind of, to start with the simple, just a real quick check on it is it still doing its job? Is it still effective? Meaning, is the dust still being captured, or you notice that there's a lot of dust coming out of the hood or dust piling up on the ground near that tool? That's your first indication that can be done by an operator. The more exact way to know is by taking duct velocity measurements. We talk about that in one of the webinars. We use a pitot tube and then either a May gauge or a velocity gauge to check the duct for design airflow. The other way of checking would be, is there dust building up inside the duct? So if the velocity inside the duct is too low, some of that dust is going to drop out of the airstream, and it'll start to pile up inside the duct. So that's all that goes into more of a duct issue, but that would be a sign that you don't have enough airflow as well. But so for starters, is it capturing the dust at the source? Is it doing its job of capturing the dust? And then in more detail would be to take a pitot tube and take duct velocity measurements to balance out the system.
Thank you. All right, next question is, whatever happened to the flex flap? Are you familiar with that?
The flex. I'm familiar with a flex hose. I'm not sure what a flex flap. I'm gonna go with. Not
All
familiar.
right. So the person that submitted that, if you would give us a little more, maybe a little more description of what that is exactly, so we can answer that question.
That's right.
So I didn't know what it was either. All right. So the next question: how about flow inducers in combination with hoods?
Again, a flow inducer. I'm not familiar with that term either. Again, but
All right, fair enough. Oh, so follow up to the Flex Flap originally came over from DCE, so it must be an older product that we're just none of us are familiar with. So I don't know how to answer that.
I apologize. There's not too many terms in the world of dust collection I haven't heard, but there's something. I mean, there's like a flap outlet that it wouldn't. There's something called a hopper outlet flap that takes the place of like a rotary airlock for highly abrasive dust, but that doesn't really relate to hoods, so I doubt that's what this particular individual is asking about. So I apologize.
That's okay. And we can follow up individually
Yeah.
as well.
Then flow inducer, I guess I'm not sure what they mean by flow inducer.
So okay, so they actually did, the person who asked that put a follow-up comment, a fan blowing at the hood. That's
Oh,
what they
I
mean by
see.
flow inducer. Okay.
Yeah, generally speaking, depending on how it's used, on a source hood, that's we don't see many of those, and you end up kind of getting between pulling and pushing, you get kind of a battle of the airflows. Where we see something like that effective is in more of ambient or large types of hoods. So a good example would be if you have a big welding shop and you have a lot of ambient weld fume, a lot of times they'll put fans just to kind of motivate the air into the airstream, but not forcing it, if that makes sense, but just kind of motivating it to get it into the collection airstream. We've seen fans behind operator blowing fume toward the collection point, weld fume or dust towards the collection point. Again, it's you got to be a little bit careful where they start fighting each other.
Yeah, I've seen it where they've used fans like, welding big metal beams, and you have your hoods on one side and you're trying to push that air because it's, there's such huge structures and trying to help assist to that weld fume going into the hoods.
Yeah, and kind of, I don't want to take it too far down a rabbit hole, but if we're talking about ambient weld fume in general, there's a couple ways to go about that. That the industry standard that's recommended is that we have the collection ducts up high in the ceilings, because that's where the weld fume is going to naturally rise anyway. But then, which most people understand, but then the other half of that is to return the clean air down near the floor and distribute it around the building in the same fashion, so that we're promoting an exchange of air. So clean air coming in from that ground level, which happens to also be operator height, deer to ear being pulled from the top, and then you're exchanging the entire building. But so that would be another, as opposed to some people use what's called a push-pull system, where you're on one side of a building, you have a big duct collecting all the dirty air. The opposite side of the building is the clean air pushing it, and it's kind of a push-pull system. We find that to be a lot less effective for ambient weld fume filtration as far as turning over the entire building. But the point of, like a fan to kind of help motivate the dirty air into the collection zone can be an effective tool in the right setting.
Thank you. All right, next question is about slide gates or blast gates or slide dampers, whatever you want to call it. He's asking, do we offer those? And if not, who would you recommend?
Yeah, we do. We have a couple of different duct companies we work with at Donaldson, US Duct and Nordfab. They both make slide gates for any size dust collection duct. We also, in the duct webinar, we'll have a little more discussion about elbows and entries and things. We highly recommend using either US Duct or Nordfab duct, because it's designed for dust collection specifically. So the elbows and the fittings and everything are designed to pneumatically convey dust through the duct, as opposed to spiral duct, which spiral duct can be very effective as well, but you have to be careful with your elbows and your fittings because you may end up in situations where you have very inefficient elbows and fittings. But the answer to the question is, yeah, we can provide all the
And they're very helpful with balancing the system. Like if you have multiple drops and one drops further away and you're trying to balance, keep the appropriate airflow, you can obviously, use the slot gates to balance the draw throughout the multiple drops.
yeah. And something else to consider, because I know you can also, the engineering firms directly or the end users or the contractors, whoever's placing the order for the equipment, often has contacts with duct suppliers. But what we found, is something to keep in mind, is that because of the discount that we're able to get through Donaldson, we can usually offer slide gates and hoods and duct fittings, through those suppliers for less money than buying them direct, which surprises a lot of people, but that is something to consider.
All right, so our next question, cost and efficiency. We talked about cost and efficiency of hoods during the presentation. Is sound a quantified consideration for each hood type as well, keeping in mind OSHA's workplace limitations? So sound as it relates to hoods, is that something that you consider too?
Since the hood's under a negative, we typically, if you get the wrong slotted hood, you could end up with like a whistling noise. But we typically don't see a lot of sound issues on the hoods. Like I said, with the only times if you have not even like a slotted hood, but more of like a gap in a hood where things are like on a built-up hood, you could get like a whistling. But again, the solution to that would just be slowing down the air a little bit. We don't typically get sound issues from the hoods.
Would you say that's more of a consideration for fan selection than hood selection?
Yeah.
Okay.
That's right. And also the return air. So going back, if you have, say, the duct on it, and again, we're getting a little offside from the hoods, but the return air, the fan itself produces noise. And then also you get noise coming out of the fan outlet. That's going to be more of a consideration. And some things you can do is to obviously have a fan outlet silencer, which is standard on every dust collector fan. And then making sure that your return air duct is a good couple diameters larger than the dirty air duct, because once it comes out of the collector, we don't care about velocity anymore. It can be as slow as possible. So if you can get it down to under 2,000 feet per minute, since it's just clean air at this point, that's going to reduce your noise coming out as well.
Thank you. We'll just wait just another moment. I think we got all of them. There's a couple questions about on-demand webinars. I might as well answer that. Let's see, is the presentation available PDF for download? It's not, but if there is, we generally don't give out the presentations, but if there's a reason why you would like it or how you'd like to use it, maybe reach out to John and let him know kind of what you're looking for and how we can help you, and we can probably figure something out for you. And as far as the FlexFlap, you can send that information to John. That'd be cool. Yeah, just shoot an email to John. We appreciate that. Thank you for some historical product information for us. That's pretty cool. And as far as the webinar, so we do have on-demand webinars available, but it's not for PDH credit because we currently don't have a way to make sure to time it, make sure that you actually watched it. But we're looking into that. So we're trying to figure out a way. We may use maybe an e-learning system, some way that we would be able to offer that as PDH credit on an on-demand basis. So thanks for the question. That is something that we're looking at. We just don't have that available quite yet. But we'll, John, we probably should, capture his name and information and make sure and reach out once that is available. Something that we're working on this year. So
yeah, and if anybody has, a group, a team that you want to feature one of the topics that are available on-demand webinars, we can always set that up with your firm and either our team or one of our we've got local representation throughout the country. We can always have somebody come to your office or schedule one if you want a webinar, and then we can give you the PDH credits. Yep.
Absolutely. All right. Well, that's all the questions we have. Thanks. Thank you to both the Johns. Good job today, guys. And make sure and reach out to John Danio if you're looking for information on any of our upcoming in-person classes around the country. We're really excited about those. And also, if you have any questions about your PDH credits or if you'd like to schedule something at your firm.
Thank you.
Have a great rest of your day.
Thanks, everyone.